Okay, welcome back. I hope you had a reasonable break. Now, so the idea now is to go through the profiling exercise on the exercise sheet, and actually there's a separate profiling exercise sheet which I will just share for you shortly, which we can go through. And now we're slightly over time here, so the idea was to spend half an hour on the profiling exercise. What we'll do is we'll take that up to, we'll take this exercise up to 2:45, and then we'll start the next lecture at 2:45, and then we'll go back into the break at 3 and in 3:15, and then finish the lecture after the break. So I'll just slightly adjust the timings. But after this lecture, really what it is more profiling and optimization practicals after that. So we've got plenty of time in the afternoon after the break to make up time from the lectures and still do more hands-on stuff. Okay, let me just share this exercise handout note. Share my screen. Okay, so on the materials GitHub page for this, under exercises, we have the full practical notes here. And as you can see in here, what we were doing earlier was the first exercise placement. And hopefully that's gone okay for most of you, but if it hasn't, let me know. We're now on to exercise 2, Cray part. And this Cray part exercise here actually has its own handout, which is called Cray part intro here. And so what you want to do is read this and go through what it tells you to do in this handout here. Now, there was some small mistakes in the source code which I've given you and in this handout for this profiling practical earlier, so I've updated these. So this one should now be fully updated. Yes, it's got the module load Cray HDF5. But if you do run into any other problems on this practical, do let me know. And because I've updated the source code, what you're going to need to do is recopy this sno.tar file like we did in the first practical exercise and pack it in here. So if you do this step here, this copy the sno.tar, which has been updated, and unpack it again in your directory and use that now, you can overwrite the existing files and use that. That should all be up to date and should work for you. But there was a slight problem in the source code for this exercise, which I needed to fix. It should all be there now. Now, I've asked about the reservation. I've not heard back yet, but I'll let you know if that reservation starts to work again. But for now, don't use the reservations on the SBatch. So that's the idea. For the next half hour, or just under half an hour, have a look at seeing if you can work through the Cray part exercise to do some profiling yourself using Cray part on ARCHER2 to take a small scientific application, profile it, and see where the performance hotspots are. And let me know if you have any questions or any problems doing that. Okay, if I can demonstrate what I get on my run, so let me just share my screen, maybe a bit clearer. Okay, so let's just have a look what I did to get here. I did a make clean and a make after I'd loaded module perf tools. And then I went into the bin directory. So this directory here, and I ran my command pat build apa vh1 MPI Cray, and that produced me this file here. And then if I go into a run directory, I modify my batch script so it calls that particular file as pat. Then when I run it, I get two things. In the output from the job, then I get this thing here, experiment. So it says CrayPat's working, experimental data directory written. It tells me where it's written it to, and it's written it to this 80871, and then this thing here. So if I look, each time I run the job, it produces me a directory with a job ID. And if I go in there, 871, we can see that there's this directory here, the CrayPat directory that is listed with a particular number in it. And in there, it's got an index.ap2 file. And so from here, if I do a pat report, of that pat report and then the name of this directory, then it will produce me the output on what's gone on here. So is that working for people? So there's two different things. There's getting the patch report, and then there's getting the thing to look at for the AP2 in let's have a look in the AP2 files. Yeah, so unless I've put up a wrong version of this document, which potentially I have, let me see what is in the CrayPat intro up here. Okay, so fine. Yeah, it's wanting you to run it on the XF file. Okay, so that's clearly wrong in the handout. Apologies for that. What you want to do is a pat report on the directory itself, not the XF file. So the Cray has slightly changed for ARCHER2 how we're doing these things. So it's on the directory itself you want to run the Cray pat report on. And then it will go in itself and find the XF files it needs and get your data out of there. So it's pat report and then just the name of the directory that was created for the output of those files. Let me update that in the documentation. Yeah, I agree. The guide is wrong. The guide is wrong. Just run it on the directory, not the XF file. And if you want to, use the apprentice tool, the APP2 tool to look at it again, you just run it on the directory, not the XF or the AP2 files, just run it on the directory. So this command here, you can't see it, but this command here has produced me a window with the apprentice information in it, this APP2, and then the name of the directory will produce your profile date. And in there, you can look at things like call trees and overall metrics of the job that runs. A little like this. This is what the apprentice tool will show you. It's a call trees, but also general metrics for the application as well, where you're doing activity across parallel processes. And see, here we've got collective operations and user time, which is normal code, and then other operations running up here. And then there's, sort of general summaries. It will give you where telling you the different bits that are going on. Hardware counters. So you can see here we've got some of the L2 hardware prefetch. We've got L2 hits, L3 hits. We've got memory traffic to and from memory. And there's also an overview it gives you where it tells you a bit about load balancing and energy usage and amount of memory used. So that is the apprentice tool. Apologies again, I will update those documentations so they look to be the right thing. And I appreciate actually that the instructions for building the APA version will also be slightly wrong there. So if you want to follow the next instructions, which is to build the more detailed profiling from after your PAT profiling, what you built before was this PAT executable here in the bin directory, and now the instructions tell you to build an APA, which is a sort of profile that is guided by your previous profiling. So it only focuses on the areas which are really important, so it doesn't produce too much data or slow your application down too much. And to build that, you need an APA file, which again is in that directory which was produced when you ran the job. So if you just go into a bin directory and you run pat build -o, and then pass it the location of that build options APA file, which Cray created for you when it profiled the last time, that will build you this new Cray MPI APA, and then you can run this one and get a different profile out from that. So can you just try it without the reservation? No, okay. I think the TA031 is the wrong way around. It needs to be TA013. So where it should be. So Luca, yeah, absolutely, it's possible to only profile one part of an application. There are different ways of doing this, but CrayPat lets you instrument your application with calls to the CrayPath routine, which will do this, or you can pass in flags which say only profile this function name. Indeed, when you do the profiling and it produces this APA file, if you have a look in that APA file, let me see if I can get that up for you now. What this will do is it tells it to profile specific functions. So here it's saying, please profile these functions by using these specific flags, say all these function names profile. And so when I run this now, it will profile things like MPI and library calls, but then it will only profile these 8 or 9 functions. And if I only wanted to profile one of them, I could delete all the rest and just profile that line function up there. But you can get much more detailed profiling if you want to do line by line stuff. There's some programmatic interfaces into CrayPath where you can insert some CrayPath calls into your source code to turn CrayPath on and off inside your application. So I've just updated the exercise sheet again, just because I appreciate it wasn't clear and was confusing about how you did these things. So apologies for that. I'll upload a new version, but I think you're all getting on with it now, and then we can start the next lecture. Any other questions, do shout at me. Do you have a question, Reese, or are you just saying you're done?
Oh, sorry, yeah, no, I was just saying that I'm ready like last time.
Thank you. Very useful. Good. I'll go on to the next lecture now. As I say, if you're still working through this practical, that's perfectly fine. You know, getting the profiling right and getting au fait with profiling tools is very useful for performance optimization. So understanding what something like CrayPath can give you, and then using it to work out where things are going wrong in a particular application or where things are going slowly in a particular application is like one of the best skills you can have for performance optimization. So do play around with CrayPath and see what it gives you. And we can come back to this practical and finish it off once we've done the next lecture. We've got all afternoon after this next lecture, really. So don't worry about that. But I do want to crack on with the next lecture so we can get it out of the way, and then you can get your teeth stuck into some actual performance optimization stuff. Stephen, good questions. Yes, here programming model refers to MPI. Yeah, so Cray is classing MPI as the programming model, the distributed memory parallelism, where you have to send data backwards and forwards. It's MPI. Is what it's saying. And if you were doing a hybrid program, it could be MPI plus OpenMP or something like that. Okay, so the next lecture is the compiler. So I appreciate you're here for learning how to do performance optimization, and we haven't touched any code yet. But the reality is that the compiler is a very important tool if you're interested in performance optimization. So, you know, almost, I would like to say first things first is profiling, and then compiler, and then hand optimization. In reality, actually, the first thing you should do with any code is compiler optimization. And then when you're happy with you're getting good and correct results from your compiler, then to move on to profiling, and then hand optimization, and then some iteration of that loop. But we start off with profiling because it's useful to understand how to profile first, I think. and it gets you a little bit hands-on with codes. But definitely the compiler is absolutely a key resource for any programmer, and particularly for performance optimization, because it's responsible for so much of that translation of your application into efficient code that runs on the particular hardware that you're using. So in this case, we're running on ARCHER2, we're running with AMD Rome processors, and a particular kind of memory and a particular kind of interconnect. And the compiler knows especially about the processors you're running on, or it should do. And so that it should be able to generate code which fits in the correct number of registers, uses the correct vector units and vector instructions, generates the prefetch instructions where possible, and these kind of approaches. Compilers are very good at optimization. There's always going to be bits of code they can't optimize, and particularly they struggle at memory optimizations and pointers and things like that. But if we can, it's usually better for us to get the compiler to optimize our code than to write in explicit optimization things inside the code. And we should hopefully see what I mean by that as we go through the lecture. Now that's because it's often, the compilers are often, that means that the code you're writing is less machine specific, because you can take it between systems, and compilers are ported between systems. And so if we can get a particular version of the compiler to produce optimal code for us, then it should produce optimal code pretty much everywhere you can run it. And then compilers break codes less often than humans, although you can quite often on a HPC system get cases where you can break the compiler, and that's because you tend to be running large codes, large complicated codes. That's sort of the outer edge of what compilers are used to. And so we do spend a lot of time in performance optimization trying to structure codes in such a way that the compilers can easily understandable and easily translate them into efficient machine code. And vectorization is, we'll talk about tomorrow, is one good example of it, because, again, we don't advocate, most of the time we don't advocate writing vector intrinsics or vector instructions, but structuring your code in such a way that the compiler can recognize vector instructions and generate them efficiently is the way to go. Compilers are complex beasts with lots of functionality in them. So a compiler will have hundreds of flags and options. Reading the man page, the manual page, or the online manual pages is your friend here. But in reality, most of these options are not to do with performance optimization. A lot of them are to do with correctness or compactness or code formatting and these kind of things, code standard adherence. But compilers do have a set of flags which are related to performance optimization, and they in particular have these optimization level flags. So -0, 1, -0, and -0, and these are not zeros here, they are O's, the letter O, capital O, and these turn on optimization levels in the compiler. So none of these are specific optimizations, they turn on sort of a group of optimizations where sort of O0 is not doing any optimizations, and O1 turns on some, and then 2 turns on some more, and 3 turns on even more, and potentially changes the order of the optimizations. Now, you may ask, like was asked earlier on the NUMA regions, if you have these flags which improve performance for applications, why don't you have them turned on, all the flags turned on all the time? Why bother with some that only turn on level 1, and some that only turn on at level 2, and some that only turn on at level 3? And there are a couple of good answers to the way compilers are structured here. Now, the first answer is that some of the optimizations that a compiler can apply have the potential to break your code, particularly around the floating point optimizations. As we discussed slightly earlier, the compiler can do things like take a floating point division and turn it into something else. Use a different algorithm to do a square root calculation. But the algorithm that it goes to may not be quite as accurate, or may change the order of operations. And for some applications, that might matter, and for other applications, it might not matter. So quite often, you go up to optimization level 3 or 4, they will turn on what they call unsafe floating point optimizations, where they will allow aggressive reordering of floating point operations. And because floating point arithmetic on computers is not infinitely precise, it has a fixed precision, or it has a machine precision. If you change the order of floating point operations, then you can change the results of your program. Now, a lot of scientific applications are not that sensitive to small changes in the results, but some are. And so turning on all the optimization up front has the potential to change results in programs and to even break programs. Turning the optimizations on also takes a compiler more time to compile an application. So some of the big optimizations can take a long time to run on big code. So if you're running that optimization with a lot of optimization functionality turned on in the compiler, it can take you a long time to compile a large code base. And you don't want that if you're developing and changing things rapidly. And then the other thing is that actually some of the highest level optimizations may not improve performance for all codes. You can see some codes that go faster at O2 than they do at O3. There is no guarantee in these optimization levels that the higher levels will benefit your codes more. They just turn on more aggressive optimizations, but it could be for your given code that doesn't improve anything and may make it slightly worse in terms of performance. So generally what we will look to do is develop our code at low optimization levels, so it's easy to compile and you don't run into any problems with the compiler changing the numerical stability or the logic of your code. Not the logic, but the mathematical ordering of your code. But you can turn, but once you're happy your code is correct and you're getting correct results, then you can turn on the optimization and give you higher performance that way. There are also compiler options which will reduce performance. So profiling, for instance, we've seen it's a useful function, but it makes your code go slower. We saw in the example on the slides, a 5% reduction in runtime when profiling. You wouldn't want that all the time, so make sure you switch off profiling when you're doing production runs or performance stuff. And then there are a bunch of other things the compiler can do for you, debugging and bounds checking, things to check the correctness of your code, which can slow down your code considerably as well. So turning these off is sensible once you're in production phase and you're happy your code is correct. If you ever run into a problem where compiler optimizations are breaking codes, I've seen that. We have a number of codes where certain compilers break certain routines in them if you have them at higher levels of optimization. And generally what you then have to do there is try and separate out bits of code which break at high level optimization, compile them at a lower level, and then link them with the rest of the code, which is compiled at the higher level. And that's a bit of a tedious process, but it's, you have to go through and work through files and then routines one at a time and try and dial up or dial down the optimization, and then structure your code in such a way that you can take the problematic parts out and compile them separately at a different level of optimization. So I've seen codes where O2 works fine for everything but one routine, and O2 causes it to crash, so that one has to be compiled at O1 level. And this can vary from compiler to the compiler. Compilers are generally designed for instruction set architectures, not processors. So they're designed for the x86 architecture, instruction set architecture, or the ARM instruction set architecture. And in fact, I remember I missed a question that was asked earlier about what would you need to do to optimize for ARM processors compared to x86 processors. And you know, there are varied answers to questions like that. You know, the ARM processors are different to the x86 processors, but they have a lot of the similar problems. You know, they're using the same memory systems, so all the optimizations we'll look at around caches and memory structuring are going to be beneficial on both platforms. They have the similar vectorization approaches, so the stuff we're going to look at for vectorization will make a difference. But once you start getting down to real low-level details of things like memory systems and registers and in order versus out of order, there are more complexities there, but you don't generally have to consider them for most applications. Anyway, compilers are generally designed for a particular instruction set architecture and then can be tuned for particular machines. So defaults may not always be optimal, so you have to check that your compiler knows that it's compiling for the particular machine you're on. And it says here, especially if cross-compiling. But quite often on high-performance computing systems, you can compile on the login nodes and run the compute nodes, but the login nodes might be different processors to the compute nodes. And so the compiler may think it's compiling for an Intel Skylake, an Intel Sandy Bridge processor, but you're running actually on an Intel Skylake, and you get lower performance than you could. Now the Crays are nice; they're set up well for cross-compiling. Actually, on ARCHER2, we're running the login nodes are exactly the same processors, I think. Well, actually, I'll check. There's certainly AMD processors. They may not be exactly the same. Let me get my. Let me just have a quick look at the CPU information here. Yeah, okay. So they are very similar processors, but not exactly the same processors as the back-end ones. So I think the front-end login node processors are AMD EPYC 7702 processors, which means I think they're slightly lower clock speed. And then the compute nodes are 7742 processors, which are the higher clock speed ones, but the same number of cores and a lot of similar functionality. So on other systems, you need to be careful that you're compiling on the hardware you're using, or you're telling the compiler what hardware you're using, and that's often done. You know, if you're on, say, the GNU compilers, GCC or G-Fortran, you do something like march equals Rome or something like that, which says this architecture I want to compile for equals, even if I'm building it on an Intel system, I can say march equals Rome, cross-compile it for that AMD system, and it will produce the correct things. Now on the Cray ARCHER2 node, this is all handled for you by the Cray programming environments and Cray modules, which do this all automatically for you. But it's worth bearing in mind if you're on other systems, or say you want to build a program on your laptop and copy it across somewhere and run it, then cross-compilation is sensible and can give you better performance, because the compiler then knows things like the number of registers that you're actually going to run on and construct your code accordingly. You know, the branch prediction functionality, the actual vector instruction set, and it can generate specific source code or specific machine instructions for those. There are also generally a bunch of things you can tell the compiler to help it in building your code, what we would call hints or pragmas, which let you tell the compiler things like loops iterations are independent, so they can be split up. Loop indexes can be independent, so they can be split up. Different memory addresses don't point to each other. Value of variables or loop sizes can be unrolled. Routines can be inline, so you can decorate your code with special keywords which tells the compiler things. Now, the nasty thing about this is quite often they tend to be compiler specific. So the stuff that works on an Intel compiler won't necessarily, will be something different on a GNU compiler. But these can be useful and worth looking at, particularly for things like the vectorization, which, as I've said many times now, we'll talk about tomorrow. Or some things like prefetching of data, or loop unrolling or inlining of routines where the compiler is not managing to do that by themselves. You can help the compiler to do it by adding the stuff to the code. Now, the nice thing is that this all appears as comments to the code in general, and the compiler just pick it up and the rest of the code ignores it. But the nasty thing, as I've already said, is it tends to be quite compiler specific. So you may have to put in different versions if you're going to be compiling across different systems using different compilers. Yeah. Compilers only work on the available information that they have. And most compilers compile code in an incremental fashion, i.e. you give it a file, it works through that file, it can work through all the routines in that file and turn them into machine code. And it can potentially look at sort of other kinds of things if it wants to do. So routinely, it treats other things as black boxes. This makes it hard for the compiler to see some optimizations it could do where you may be using the same variable in two routines, and it could put those routines together, or it could optimize inline your code into another routine if it knew that code you're putting in didn't affect any of the data structures, and these kind of things. So there are things you can do here, like telling in your code using sort of language features like intent or pure, intent in, intent out, or pure in Fortran, which tells the compiler things about what data is being passed in and out and whether it's going to be updated, or whether this function or subroutine will impact any other memory elsewhere in the program. And that allows it to do things like move around instructions more and give the hardware more latitude to move instructions and combine instructions, or do copy data but not copy it back out again, so you don't have to use extra memory traffic. In C and C++, you'll see a lot of use of a const keyword, which is actually this parameter I'm passing in, but it's not going to change. So again, it's like a Fortran intent in, where I can get rid of, I don't have to copy the data back out again once I've copied it back in, and these kind of things. And there are compiler hints and command line flags that can help with this. So one particular big one here is something called interprocedural optimization, IPO, which tells the compiler, actually, can you not treat all the routines and black boxes, but try and look across all the routines and see if there's things you can do to optimize between them, and potentially do that between files as well. Now, again, this is a very powerful piece of functionality for the compiler, but we don't tend to do it by default because it takes a long time, adds extra complexity to what the compiler does. And it also then requires extra things like more memory and more computational resources. And we can often see this for big codes breaking the compiler because it just can't handle that level of interprocedural optimization. So we use the compiler, we try and use the flags, so turn up the optimization, turn on specific optimizations, and then pass in hits to the code, from the code to the compiler, things like Pragmas and pre-processing directives, which say you can unroll this loop, inline this bit of code. These function calls are safe. This data structure doesn't point to that data structure. We can do all that. And that can improve the performance, but if we still have performance issues that we need to tackle, then we'll have to get hands-on with the code and do actual code modifications. But code modifications, of course, are hard. They're generally, the scope there that they introduce bugs. they make the code hard to maintain and read, which is a significant cost to a lot of codes, right? You know, so making your code go 5% faster may be a great thing, but making your code 10% harder to read and maintain in the future may make it more expensive and not worth doing. There's always a trade-off between the cost and the benefit of these things. Now, if your code is run by 100 people, and each time they run it, it takes 1,000 cores, and it's run on HPC systems around the world, then obviously optimizing that 5% on your runtime is going to benefit because a lot of people are going to save time overall. And so it's worth making the code harder to maintain and understand and debug and these kind of things, because you can afford to pay that extra cost because the benefits are high. If you're just writing a small code for yourself, and the difference between optimizing 5% on it is it will return the results to you 5 minutes quicker, then it may not be better to do that. So it's always worth thinking about, you know, is this optimization really required in the general scheme of not just performance but maintainability and portability and correctness of your code. But what we're going to talk about in this lecture is what is the compiler actually doing for a lot of these optimizations, and then there may be ways you can rewrite your code to let the compiler do the optimization more and achieve it when it's currently failing to do those kind of optimizations. Okay, how do we do this? Well, you know, for key routines, we can actually have a look at the assembler code and say, let's produce the sort of the machine instructions or what will get translated into machine instructions the compiler's producing here, and see what that looks like. And you know, there we can do things like, okay, I can see it's translated this line into 15 loads, you know, 7 additions and 5 multiplications and 4 stores. But I think, you know, looking at the code, that should be able to be done in fewer instructions than that. So what's going on there? So that's a bit hardcore. At a slightly more user-friendly level, you can get the compiler to tell you things about what it's doing. So you can get it to give you an optimization report, and in that optimization report, it will tell you, okay, I've unrolled these loops here, I've merged these loops here. I wanted to unroll this loop over here, but I couldn't do it because it looked like it wasn't safe. And then you can find those places where it's trying to do an optimization and failing, and change your code to do that. There are also some performance modeling approaches which are useful in terms of working out how good your code is, and one that's quite often used is something called a roofline model, where you look at the underlying hardware performance of the system you're on, and then you look at how much theoretically your code should get on that. So, you know, for the key computational kernels, you can look and say, well, in here there's 20 loads and 10 stores and 50 floating point operations. So I can work out the arithmetic intensity of this, so how many floating point operations you do per load store, and then you can situate it on what the hardware itself can do and see if you're close to that or not. And then you can also, you know, play around a little bit. So you could take one quite nice thing to do is take your code and compile it with vectorization options turned off, and then you can see what's the performance difference when the compiler's vectorizing. And if you can, you know, on a system like ARCHER2, if you can see, you know, significant performance difference, 4 times slower, 8 times slower, then you can say your code is optimizing well in the vectorization space. Whereas if you turn it off and your code performance hardly changes, well, it looks like your code's probably not vectorizing well, and that would be a good place to have a look at performance issues. Particularly, you know, if you can do that alongside some kind of examination of performance through looking at cache misses and things like that. Okay, so if we get into the guts of it, and what I'll do is I'll speak for another 5 minutes, then we'll break the lecture here, have a break, and come back and finish the lecture, and then get back onto practicals. Just so you don't have to fall asleep to my voice too much. So one of the things that makes a compiler hard to optimize your code, makes it hard for a compiler to optimize your code, is the sort of scope of variables. Local variables, variables in a routine or defined close to the scope of an application, close to the scope of its use, make it much easier for the compiler to reason about whether it can make changes to that variable and whether it can make changes to instruction ordering and things like this. So if you use global variables, the compiler has to make worst case assumptions, things like the global could be modified by any call procedure or any other thread. So in general, global variables are to be avoided in terms of compiler optimization if possible. Use local variables and then automatic variables where appropriate. And automatic variables are those defined inside functions themselves, because these are more efficient ways of enabling the compiler to do the optimization of the application. And in C specifically, looking at file scope globals is better than externals or sort of whole program globals. Another place where performance can be lost, both in terms of the compiler, but also just in terms of general performance, is conditionals. So branches, particularly if statements or switch statements. Now, we've already talked about the processor, and generally it has hardware inside it for predicting branches and predicting what branch will come next and doing speculative execution. But even then, it's likely to have performance impacts on your application, particularly if branches are called very frequently, and particularly if the outcome of those branches is quite random. Now, I appreciate it's a code; it's not going to be random, but I mean non-uniform in the outcomes. And so, code cannot generally be written without branches, but the idea here is to look and see if you can restructure your code to remove branches from some of the most computationally dense parts of the code. Here's an example here. Try to avoid branches in innermost loops. So here we've got a loop here over some Fortran code. We've got a loop, and inside it we're adding one number to another. And this is a kind of bit of code that you'd like to see, particularly if K is big, vectorized and giving you good performance, because it's the kind of code that vector processors work really well on. But it's got this branch inside here, and so this branch is going to generate extra instructions, potentially pipeline drains, and all these kind of things going on here. And so if this branch doesn't need to be here, then getting rid of it will give us better performance. And in this case, N doesn't change inside this loop. So, I can get rid of this branch from inside the loop, still maintain the branch, get rid of a branch from inside the loop, and now I've got one branch call here, and then hopefully a large number of loop iterations inside here. Now, this loop as well does have a branch at the end of it, but the branch prediction hardware is very good at predicting loop iterations. And so this branch is not as expensive as this branch up here that we had before. So moving this branch to the outside and then having two versions of the loop, one which says, one that says if n is equal to 0, do this, else do that, I can improve the performance of my application here. Now, of course, this is not brilliant in terms of code programming, because you've now got a bit of code duplication. It's now, instead of having one loop, now I've got two loops, and I have to maintain those separately. but it's not a huge overhead for me in terms of a programming approach, and that has the potential for good performance improvements. Now this one here, the compiler will probably be able to do this for you. It's a pretty simple bit of code, because n equals 0 is not changing inside the loop. You would hope a good compiler can do this for you. But compilers are not necessarily brilliant at doing more complicated loops with complex loop and branch conditions, or loop, not loop, if conditionals, or if these are sort of things that they can't quite work out. So a compiler, if there's a pointer in here, or a memory structure which is coming in from outside the application, the routine or function, but it's going to be hard for a compiler to safely reason this. Whereas here, as an application developer, I can say, well, if I can get rid of a loop altogether and just say, actually, do I up to j, and then I from j up to k, and I can get rid of that branch altogether. And it's unlikely the compiler will have been able to do this for you, because it can't really reason about the logic that's going on in here. Right, before I jump into data types, I'm going to leave it there for half an hour. We'll have our coffee break now till 4 o'clock. Then I'll come back and finish this, and then we can get cracking on finishing the profiling exercise if you haven't finished it, or moving on to the next exercise, which is more hands-on optimization on actual code if you have finished it. So we'll start again at 4. Give me a shout if you've got any questions. Okay, so I'll finish off this lecture as quickly as I can, and then you can get back to playing with some code on the system. As always, just drop in questions when you have them. And if you're struggling with any of the practicals still, let me know. As I say, more than welcome to drop me an email or send this message to me. Okay, so another area where performance choices you make in your program can affect performance, of course, is around data types. And there is actually, of course, a range of performance impacts from choosing your data types you use. So a difference between 32-bit and 64-bit arithmetic, both an integer and floating point. In terms of how much data you can move to and from the processor, how quickly, and then how quickly the processor itself can work on those bits of data and work on those instructions. There is actually a growing body of work, particularly around machine learning, where fixed floating point numbers or integer arithmetic on smaller data types is being more widely supported. So actually we're seeing in a lot of the newer processors support coming in for 16-bit and 8-bit floating point or integer operations much more aggressively now in the hardware. But in reality, if you can use a 32-bit over a 64-bit floating point number, i.e. if you only need precision down to, say, 10 to the minus 8, then you're always going to get performance benefits by using floats instead of doubles, or real 4s instead of real 8s in Fortran, because you're going to get twice as much data loaded into your cache for every time you load a cache line in, and you should be able to do vector operations with twice as many twice as much data in them. As a general rule, avoid unnecessary type conversions, so ints to longs or floats to doubles, because that's going to cost you some time both in the processing pipeline and just as instructions to do. But you can get away with reducing variables down to smaller sizes, from 64-bit to 32-bit, double precision to single precision more efficiently. Compilers have a good, generally quite good at doing what we call CSE, or common sub-expression elimination, going through your code and getting rid of places where you're using the same sets of variables and the same sets of operations or functions, and getting rid of the unnecessary operations. So if I had a look at this example here, d equals a plus c, and then e equals a plus b plus c. Now the compiler can generally deal with these kind of things, but here it's a little bit harder, because a plus b plus c, if you'd written this as e equals a plus c plus b, then it could have said, actually, I've done this addition here, and that down here I can just say e equals b plus d and get rid of the a plus c, and we get rid of one operation and speed our code up there. But compilers do struggle there a little bit in this sort of common sub-expression removal if you've got changed the order of your operands between the calls. So if you can write it in such a way that a compiler can make it easy to see, or indeed just change the code, so d equals a plus c, e equals d plus b, that will be a more efficient piece of code. And also the compiler finds it hard to do this common sub-expression elimination using functions, because it doesn't really know, unless you've told it specific things about the functions, like in Fortran saying that it's pure, that this function will produce the same result every time you run it. Whereas if you'd have stored this into a temporary variable, b equals func c, and then d equals a plus b, e equals, b was the wrong variable to use there, sorry. Let's call it f. F equals func c, d equals a plus f, e equals b plus f. And that will get rid of this expensive function call, only do it once instead of twice. Good. Now, so I see there's a question in the chat. Is there a penalty for conversion between signed and unsigned data types of the same type, of the same sizes? No penalty. It will cost you an operation, but there's no real performance penalty in doing that, no, because you're not changing the size of the operations going down the pipelines or those kind of things. You're not interrupting the process of flow. For the second case here, where you want the compiler to eliminate multiple calls to the same function because it's producing the same result, the compiler really needs to know things like the function always returns the same value for the same input, and the function doesn't cause any side effects that would change, sort of modifying inputs or changing global data. And so this is where you would need either nice function prototypes to allow the compiler to know this, or using language features such as in Fortran, the pure keyword, which says this function does not change any of its inputs and does not change any global state. Otherwise, the compiler has to assume it does. And in C, you can make sure that you're passing in consts inside the function. And now I think there is a similar keyword in C to the pure in Fortran. I can't remember off the top of my head, but I'll have to look that up and come back to you on that one. We've already talked on one of the areas of a processor which may restrict your performance is registers. So compiler generally does a pretty good job of register allocation. We only have a certain number of registers, which if you remember, are these temporary storage places on the processor where the data that's currently being worked on is kept. So if you end up with loops with large number of temporary variables in them, loops such that have been inlined or unrolled, so some of the optimizations the compiler does it itself, or you may do for it, can produce this. Array elements with complex indexing expressions, and these kind of things. Then you can get register pressure, which may slow down your pipeline because the processor says, well, I'm going to have to wait until some of these instructions are finished to clear out these registers before I can get new data in. So there are ways around this. So you can do something like include an explicit scalar temporary. So most compilers will use register for explicit scalar temporary. So what do we mean here? Here we can take this code where we can see we've got some complex index arithmetic here, where we're going to have to get I and C of I and then A off the back of that. And then we've got C+1 down here. And that can mean that we're using more registers than we want to here, because we're having to store C of I in here as well. Then you can change this code. So because C of I just goes up, let's say linearly, let's assume that C of I just goes up linearly. So we can replace C of I with a scalar temporary. Here, then we can say here we've got temp equals the beginning of an array, and then if we know that this array just goes up by 2 every time, we can replace it by this scalar temporary in here. So temp equals temp times I, 2 times I, and that will just replace that. Now, in reality, in terms of looking at this as a pure loop, we're not helping ourselves in terms of registers. We're not helping ourselves in terms of registers because you need the same number of registers to store C of I here as you do to store temp. But once you start pipelining this into a longer thing, a longer set of instructions, then we can see that we can eliminate some of the need for the temporary variables in between time, and away we go. Yeah, if a compiler runs out of registers, it generates what we call spill code, which is store a value and then reload it later on. And so what this is doing is saying, okay, we've run out of registers, we can either stall the pipeline and wait, or we can move some data around. And if it's generating spill code, then what it will do is take your data and that's in registers waiting to be used or waiting as part of a pipeline, and move it into a L1 cache. Now, L1 cache is very fast, but it's not free. It can take 4 instruction cycles to get data to and from L1 cache on these AMD processors. And so it will introduce some kind of overhead by doing this. So it's not going to be a full pipeline stall. It's not going to be 19 cycles, but it could easily be 4 cycles repeatedly, which will reduce your throughput by a factor of 4 potentially, depending on how often it occurs. And so one way you can see this is actually looking at how many loads and stores are required in your source code, and then compare it to what's happening in the assembly code. And if this is happening, if you're having many more load stores, and you can also look at this in terms of instruction retiral rates when you get profiling data back to say how many instructions have been finished per clock cycle, and you can start to see lower numbers of instructions being retired than you would like. Then if this is the case, what you may need to do is distribute some loops. So that is split up complicated loops into smaller, simpler ones. Now, it's interesting because there's an opposite optimization you may have to do sometimes, which is combine 2 loops together. You might want to combine 2 loops together because they use the same data and you want to reuse them efficiently in cache. But there can be times when you want to distribute loops or split a big loop into a set of smaller loops if you're running into issues like this register pressure, register size things, because those loops have too many things going on in them, and you can split them up into separate loops, particularly if the work is independent in those loops, and enable the compiler and the processor to do a better job of utilizing the hardware it has. Loop unrolling and pipelining are very important for the processors we use at the moment. Compilers are very good at loop unrolling, but sometimes they don't work. And so you can look at the reports that you get out of a compiler about how well a compiler is doing and what kind of loop unrolling and these kind of things it's doing, and you can find loops where it's not unrolling loops. And you could go and unroll those loops by hand, and we'll see what that means. But it's easier if you can is to try and fix why the compiler can't unroll it. So it should tell you I can't do this because of a dependency or because I don't understand this. And that is a more portable thing to do. Yeah, so the reason why we want the compiler to unroll loops generally is that for every loop iteration we do, there's a set of bookkeeping that we have to do at the beginning and end of loops to add one onto a loop variable, check if the loop is finished, and if not, go back to the beginning and start the loop again. And if our loops are small, there's not much work inside them, then those overheads of doing that bookkeeping, integer operations, the comparisons, can be quite high compared to the cost of doing the work inside the loop. So by unrolling the loop, by say doing 4 iterations of a loop at once, we can then reduce that bookkeeping overhead by a factor 4. And that means we get much better performance through our loops. It gives more scope for scheduling instructions and for scheduling the integer instructions alongside the floating point ones. It reduces the number of times you have to check whether the loop is finished. And it makes more independent instructions for multiple issue for superscalar things. So here's an example. I've got a loop. It's doing a reasonable amount of work here, but not loads of work. So in this loop, I've got 2 floating point operations, a multiply and an add. And I've got 2 loads and a store. And then for each time that I run that loop, I've got an integer add and an integer comparison. So I've got, say, 4 floating point operations to 2 integer operations. Whereas if we unroll the loop and say actually do loop over this by 4 times, we can now see, this is manual unrolling it, this is doing it by hand. We can now see here I've got 16 floating point operations, 8 in arithmetic ones and 8 load or store ones. And in fact, actually, it's more than that, isn't it? Because it's two loads and a store and 2 mathematical operations. So it's 5 per iteration. So we've got 20 floating point operations here for every time we have to do 2 integer operations down here. So we can see that allows us to do much more of our core work without having to hit this overhead of doing the loop. And particularly important because, of course, this down here is a branch, and now the branch prediction hardware will do well, but we still don't want to have to pay the penalties of that branch prediction hardware more times than we need to. Now, of course, we can't just unroll this loop without taking care of the loop bounds, because unless the loop exactly divides by 4, we've got to have a special spill loop or remainder loop at the bottom here to finish the last few iterations in case the loop counter doesn't divide by 4. But here the loop has manually been unrolled by 4, and generally the compiler will be able to do these kind of things for you. But it's done at the compiler or intermediate or assembly load level, and it's reliant on the compiler being able to say, actually, if I do this instruction 4 times on different bits of data, is there any side effects? So there's got to be no dependencies between this. We can't have, say, A of I equals A of I minus 1 plus B of I, because then the previous iteration depends on the current iteration. No, the current iteration depends on the previous iteration, and I can't do them all at once. And so those are the kind of things which will stop the loop, the compiler unrolling the loop. So we need the loop iterations independent, and then the compiler will do unrolling for us, usually by a factor of something 2, 4, 8. Now we can generally tell the compiler what to unroll by. We can set a global unroll factor or a loop unroll factor through compiler flags or pragmas or comments in the code. But again, you may ask why. Well, okay, if this benefits me going to 4 times unrolling, why not go to 8 times unrolling or 16 times unrolling? And again, this is because we start to run into other problems then, where we run out of registers to store temporary data in, and we get register pressure there. So those are kind of things. Now, a compiler will also generally try to unroll inner loops, but it is possible to unroll the outer loops if that improves locality, so temporal locality of the data. Now, this is a little bit of an interesting loop here, because in Fortran, this memory index on a multidimensional array. The first one is the closest in memory, so it's the one that's stored closest in cache. So this is the one we want to iterate over, whereas actually we're iterating over this inner loop here, this J loop. So from a memory point of view, this is not the nicest way of doing it. So every time we go around this loop, we're going to have to do more loads, and actually more loads from potentially distinct areas of memory, so more cache lines. Whereas we cannot manually unroll this outer loop and say, do 4 of the same I's for each J, or 8 of the same I's for each J, or something like that. And that can give us better cache usage and better temporal accounting. This is the kind of thing the compiler generally won't do for you, because it's harder for it to identify these kind of things. There are a couple of things we can do to get rid of dependencies between loops. So one is variable expansion, and this is also maybe potentially around reduction variables in loops. So where we're summing things up in loops, that would be seen as a dependency as well. So here we've got we've got A going around this loop, and we're adding it up into a reduction variable B here. So every time we go around, we add up a value of A into B and continue. So by the end, A will be the sum of B will be the sum of the whole array A. This is fine, but you can see that each iteration of the loop is dependent on the previous one. So B of now of I equals 1 depends on what B was on I equals 0, and so on and so on. So the compiler won't easily won't unroll this loop, because we have these dependencies. But actually we can do things to expand this variable to unroll this loop. So actually instead of summing up into a single variable, we can sum up into multiple variables, B1 and B2, and actually we could do B3 and B4 and unroll the loop 4 times. And then at the end we have to just add in this extra single line to add all those temporary sums together to give us a global sum. So there are ways around these dependencies which may restrict areas where a compiler will want to do things like unroll a loop for optimization point of views, but can't do that. Compilers may also do register renaming, but we don't need to care about that too much, because this is internal to what the compiler is doing. This may mean that the compilers end up using more registers than you think, just because it's trying to do that to allow you the different instructions to be scheduled separately. So we can see here that what we're doing here is storing and adding data to each other. So here we've got an addition where we're adding this number onto another number and storing it into a particular variable. And we can actually use multiple registers to do that, to try and temporary registers to do that, to try and get around. So we can do 2 additions at once rather than having to wait for the result of that and then bring them together. Yeah, so software pipeline can also be a useful technique where we can try and construct basic block that contains instructions from different loop iterations. So we've got different loop iterations, and we're trying to effectively build a pipeline in our code to keep data running through them. So this kind of operation here, where we've only got a small bit of a loop going on here, there's some a small amount of working going on in this loop, and ideally we would unroll this to get us higher amounts of work for this loop. But another way of doing this is to pipeline this loop, so we actually end up doing part of this iteration and part of the next iteration each time we go around the loop. Then we can end up doing 2 iterations per loop. Rather than unrolling it, we can end up doing 2 iterations per loop rather than a classic unroll. And that can be nice in terms of spreading out the dependencies across the loop cycles and spreading out the usage of different functional units. So the idea is possible to start executing instructions from the next loop iteration before the current one is finished. And that means there's fewer dependencies between the instructions in a given block, which lets the compiler do a bit more scheduling of instructions more freely, because it understands how to do that. And so we move from this thing where we have a pipeline stall on the store to the FAD by moving them into different places, and that lets us get around some of these dependency hazards in our instruction pipelining. So as we've said, some of the impediments to unrolling are things like function calls in the loop, barriers and branches in the loop, so if statements or go-tos or jumps, and compiler can't be sure if you've got a lot of pointers or array aliasing in the loop. So looking at what the compiler has been able to do, and then seeing in the report which loops it can't unroll, and then go and have a look at them and see if you can fix some of the issues it doesn't like, can be really good. So here's an example here in C. We've got an array here which has got an indexing variable which tells you where to go in here. And now we could unroll this loop, but the compiler doesn't know where index I points to. So it could be that index I for 0, 1, 2, and 3 all point to the same place. So it doesn't know how to unroll those. And it also could be that IP and index I overlap at some point, so it doesn't know how to do this. So we can get around this by moving in the IP outside the loop, or by telling the compiler that this is a permutation or some kind of scalar temporary on the loop index itself. So there's some kind of permutation of I, and we'll see that in the vectorization practical tomorrow. Or by just telling the compiler that this loop is independent, and then it will unroll it itself. Okay, we're coming towards the end here. You'll be glad to know. But compilers, another bit of functionality which is useful for them is inlining code. This is taking functions, and instead of running them as separate functions, it's effectively copying the source code out of them and putting them directly into other functions. And this is nice because it gets rid of that function call overhead, and a function call is an expensive thing to do in a program. There's all sorts of operations that have to do to go on to take the function and set up its stack and move data in and move data out and interrupt the function pointer, all these kind of things. Now you could do this yourself by hand, by pre-processing macros, and by rewriting your code. But there's lots of reasons why you might want to write functionality into functions, from testing and benchmarking up through to easy documentation and easy maintainability. So what we'd rather do is get the compiler inline as much of the small functions as we can, where the function call overhead will significantly impact performance, particularly in things like object-oriented code, C++, and stuff like that. The object-oriented design methods can quite often let you have very large numbers of small function calls, getter and setter methods for each data element, for instance, which can kill your performance. But if you can get the code to inline those functions, then you don't see that kind of overhead. Now, in general, the compiler will try and do inlining of codes of functions up to a certain size if it thinks it can. And you can change what size it should inline. You can change, up to a few hundred lines, up to 1,000 lines, or down to 10 lines. You can make those changes with compiler flags. And it's also what you generally also need for that is good interprocedural analysis, which we will talk about. It's this idea of letting the compiler not just optimize a single function call, but optimize, as we say, across all the functions in the program, not just inside a single file or a single function call. Now the compiler is also may need to get the best level of optimization out of a code. The compiler may need to do multiple things at once. So it may need to do inlining, then loop unrolling, then common sub-expression elimination, and those kind of things. And that might also stop the compiler doing its work, doing good optimization, because it may just run out of the ability to do too many optimizations on the same bit of code. Both for time reasons, the compiler doesn't want to take too long to compile for you, and for resource reasons, it may just run out of, it may have a fixed amount of memory to do the compiling. So you may be able to do so it may be that for some bits of your code here get very complicated. Ideally, we want the compiler to do everything, but you may want to do some of them by hand, do a bit of the unrolling or a bit of common sub-expression elimination, or a bit of the inlining by hand, which could let the compiler do a better job of doing the rest of it. So yeah, that's that. But there again, we want to do this in a nice, controlled fashion. Try each step in isolation before trying to combine it with hand optimizations. So try getting the compiler to do all the inlining and see what that does, or get the compiler to do the unrolling and see what that does. And then that will give you an idea as to whether you need to spend more time doing some of this manually. If both inlining and unrolling separately give good performance benefits, but when you try and move them both together, you don't get the same performance benefits, then it may be that you have to help the compiler there by making some code modifications. Okay, so talking of compilers, we have 3 compilers on ARCHER2. We have the Cray compilers, which we've been using already, and they're the ones that are loaded by default. And so that's the Cray C and Fortran and C++ compilers. We have the GNU Fortran C and C++ compilers, and we have the AMD Fortran C and C++ compilers. That's slightly different from the previous system, which was Intel compilers, GNU and Cray. And also on ARCHER2, Cray have changed their C and C++ compilers. So they're no longer the Cray compilers, they're now based on Clang and the Clang source code tree, which is actually quite nice because so is the AMD compilers, so they're quite similar in their operations. Now the Cray have made some changes and modifications and extensions to their C compilers, but fundamentally they're based on that whole Clang LLVM underlying system. Okay, so what does it look like what are the compiler options for the Cray compiler? Well, we have these -02, which is the default for Cray, and -03 for even faster. And then we can see things like interprocedural optimization to enable you to do inlining and some more aggressive across function optimization. Then you can have a look at producing listing files or source files with information about what the compiler's done to that. OpenMP compilation, which is on by default for the C compiler, and you can turn it off with the H, no OpenMP, no OMP. And then some of the threading directives you can do there as well. For the Cray compiler, generally, it's pretty fast as it is, but if you want to try it out, you can turn up the optimization by using something like -03, FP3, which will turn on some more aggressive floating point optimization. But if your application is intolerant to floating point reordering, like we've talked about, if you're really sensitive to machine precision operations, then you can turn that down as well. So -H, FP1 or FP0. Yes, and it's unlikely that the highest level optimizations will be that beneficial for you. OpenMP is on by default. So on the Cray compiler, not on the GNU and AMD compilers, but the Cray compiler, so you can turn it off, as I say, with this flag here. But there also is functionality to do auto-threading in some of the Cray compilers, which is not the same as OpenMP. I've not played around with it, but it's not on by default. You could have a look at it if you wanted to. Of the other compilers, the GNU compilers are great, but they tend to be quite conservative in terms of their performance optimization defaults. So in general, they're sort of -01 by default, and what you want to do is turn on higher levels of optimization to get better optimization, so try -03 and those kind of things. The AMD compiler, we haven't had loads of experience with, but we have had some experiences. It's quite like the Cray one. It gives reasonably good performance out of the box, but there are some options to do more optimization or less as required. And you know, there's some of this on the website, but this is the sort of ideas. If you really want to have a look at the aggressive optimization on GNU and AMD, then -0 fast is probably the way to go. And we can look at the vectorization options as well, which we'll look at tomorrow. But there's some of the, you know, some of these may be useful for your applications, and some of these it's always worth reading the manuals because these change over time for new releases of the compiler as well. So the compiler is our friend. We want to use it more often than we want to change the code if we can. So compiler flags are the first place to start with any optimization, and then looking at the reports out of the compiler to tell you why it's not giving you good performance. And then you can then look at profiling and then go on to do performance optimization. And so we've got to try and help the compiler do its job. And you know, on that note, it's always worth trying multiple compilers. So we've got 3 on Arch. You don't need to use all 3 of them. But if you're porting and optimizing your code, it's always worth running on at least 2 compilers to see if you get comparable performance and if you get the same correctness, and if one compiler is better than another for your application. You know, on the Intel processors, the Intel compiler is quite often give you 10–15% better performance, which is worth having. We'll see if the AMD one does for Archer soon enough, but that's always a sensible thing to do. And if possible, minimize code modifications in the first instance, and then we can get on to profiling and work out which bits of code we really want to change and take it from there. Any questions? So I do apologize, you've listened to me for quite a long time today, and so well done for maintaining concentration if you have managed to do that. I'm not going to give any more lectures today. We've gone over the lecture time by a reasonable amount of time, but there's still an hour left between of the day where, if you want to, you can go through and do the exercises. So there's a finishing off Cray profiling exercise, which is great if you can get the performance reports and try the APA profiling. I would really suggest you do that. And then if you have a look at the exercise sheet, we can go on to exercise 3 on not the Cray compiler exercise sheet, but the practical notes one, which is to take a bit of source code, which is not parallel, but is so it's to go through the compiler optimization exercises in exercise 3, and then if you finish those, there's the optimization exercise in exercise 4, which is a more long-term, bigger piece of work, which is basically to take a rubbish piece of code and make it go faster, first using the compilers and then using some of the stuff we'll talk about tomorrow. Gunnar, is a great question. How interoperable are compiler hints between different compilers? Unfortunately, not very interoperable. So some of them, if you can use them from external sort of standards like OpenMP, so if you can use the OpenMP SIMD directive to tell it that loops can be vectorized, and that can be great. But in general, the other ones aren't hugely portable between compilers. So GNU will have a different thing to Cray. And there's probably a reasonable amount of standardization between GNU and the Clang compilers, the open source ones, but there's still some variations there, so it's a little bit annoying, I'm afraid, in that one, which is why using compiler flags to start with, if you can, is a good place to start, because you can easily find you don't have to change that in one place, and you can easily find the reference for the other compilers' similar flags. But it's a good question. Any other questions? So I'll put in the chat here a few references for finding these equivalent hints. I don't think there's a directory, but a dictionary, but I'll have a look. I'll have a look. Reese, great question. Blackboard collaborate crashes if swapping tabs on Chrome. I've not seen that, but I can ask around and see if there's any tips. Alan, let me have a look. It should definitely be there. He says. So the compiler exercise sheet is on the website. Hopefully you can see that. No, okay, sorry, that's my bad. It's inside it's in the subdirectory of the SNO, yes. Apologies again, that's another mistake. But yeah, it's not a separate compiler opt, but I can copy it in there so you have it anyway. It's inside, I put it inside there. Inside the SNO one. There definitely are no Intel compilers on ARCHER2, Yevgeny. There's no Intel compilers that are centrally supported, but you can install them yourself. So I've installed my Intel compilers on ARCHER2, and I played around with using them. They work fine. If anybody's actually interested, this is not officially supported, but the Intel compilers are installed here. No, so it's not something I'm suggesting you want to do as part of this exercise. I've installed the Intel compilers here. Okay, I will fix that. The exercise sheet shouldn't say Intel compilers. It's just okay. Yes, it says Cray compilers and then it says Intel compilers. I'll fix that. If anyone is interested, I have installed the Intel compilers on Archer, and you can use them like this. As I say, I'm not suggesting you need to do that on Archer during this exercise, but if people are interested in the future, you access to the Intel compiler. Getting it to work with the Cray MPI library is a little bit more complicated, but if you're interested in that, let me know, because that's something I've done as well. So you can actually use the Intel library as well. The MKL libraries are not available by default. They are in that install, but the ones we use to replace MKL on ARCHER2 is Cray libsci, which is loaded by default, and does a pretty good job compared to MKL, but Cray libsci is the Cray version of that. David, you shouldn't have to unload any of the modules in exercise 2 before starting exercise 3. Because the perf tool stuff won't get called unless you explicitly do the pat build thing. So I think it should be fine. But good question, and I could be wrong. It may be that it does change something. Cray libsci should support the same function names in that MKL doesn't generally have this, the MKL just does function names from things like BLAS and LAPACK and SCALAPACK, and so Cray libsci does the same. Of course, it won't support some of the MKL specific function names like you do in MKL grid info and those kind of things, but it should do. If you have any specific questions about, or problems replacing MKL with Cray libsci, then do let me know. Yeah, I mean, Cray, it depends what the functionality you need it has. The Cray libsci does have a lot of stuff in it, but there may be specific things in MKL that it doesn't. I've not myself come across too much that we can't do in Cray libsci. But if you have specific questions about specific things, then let me know. There's a good overview. I know it's someone else's site, so maybe I shouldn't use it. There's a good overview from Oak Ridge on their libsci install, what it has in there. So there's LAPACK and Skill APAC and FFDW, stuff like that. And then there are some Cray specific things in there. So that may be a place to have a look at to start with. But if you have specific things you're using, I can always look up and see what would be sensible to use on Archer, if that's useful. As a little aside, this website here is also quite useful for looking at compiler flags. So this comes from Clang, the Fortran version of Clang, but it has quite a good set of compiler flags across multiple compilers, including the Cray, GNU, and Intel. So if you've been using Intel compiler elsewhere and want to look for a flag which would map onto the AMD compilers or onto the Cray compilers indeed, then some of this stuff is quite well listed on that side. So I should say, as mentioned before, because you have access to a system for longer than today and tomorrow, and you more than welcome to do the practicals in your own time. You don't need to hang around here. It's just I'll be here if you've got any questions. If you want to pick up the practicals again tomorrow or later in the next week or the week after, that's perfectly fine. And tomorrow you can continue these practicals if you want, or move on to the next practical. So there's plenty of flexibility. I was going to do a little summary at the end of today, but I think I've spoken enough to you all, so I won't summarize. But feel free to leave. I'll hang around till 5:30 if you've got any questions. But if you want to get on and do other things, that's perfectly fine. And if you want to stay here and do the practical, that's great too. Thanks for coming along. I hope you had a good day, and we'll see you tomorrow at 9:30 for the OpenMP lab.
Hi, Adrian. Thanks for today. It's been really good. I have a very peculiar question. You might not be able to answer, but I thought I'd give it a punt if that's all right.
Right away.
So I'm a sysadmin at Sussex, and a couple of our users have started using Julia for doing machine learning applications, and Julia has the ability to use compiled C code, which gives great speed ups. But I was wondering if you know of anything to do with that integration between Julia and loading C code that might give us hesitations in compiling it with different compiler flags for optimizing it as much as possible.
In general, no. I mean, in general, once you've got down to the compiled code level, so it's produced instructions which can then be linked into a different application, then you shouldn't really have any problems like that. So Julia should be pretty capable of linking in and utilizing code with high optimization levels as well as low optimization levels, and code across different compilers. How susceptible to changes in results Julia will be for changes in program optimization is an interesting question, and not one that I have any real experience on. But you could imagine that a library where it is doing its own sort of maths and its own sort of storage of data in different data formats, there may be a little bit more of a chance that you may get these kind of numerical issues. But on the whole, I mean, the performance we've seen with Julia across a range of applications and a range of systems is very good. And I don't think there's any reason to believe that you couldn't get the same as C performance or close to C performance with good compiler flags than you would be able to do with a vanilla C code on something like ARCHER2.
Brilliant. Cheers. Sorry. Just in case there was something that is glaring that we missed or that was a known issue, I thought I'd ask an expert. Thank you.
No, I'll have a quick poke around. I know there are people doing Julia performance stuff, but I don't see any reason why there should be any issues. It would be nice, actually, it'd be a nice little thing to do on ARCHER2 is to see, how well Julia performed with the Cray compiler versus the GNU compiler versus the AMD compiler. Maybe try and get some students onto that.
Envious of the ability to use students. I love it.
Well, I don't know. They tend to often be as much work as they are produce work. It can be a nice resource sometimes.